Welcome back to video 2 of the central dogma theory. You just dove into looking at the difference between DNA and RNA structurally. What do they look like? How are they different? And so today we're not actually, now, not today. Now we're going to look at, well, why do we care about the differences between DNA and RNA, and how are they playing a role in the production of these traits that we see. And just to clarify, traits can be anything from the fact that I have 5 fingers on each hand, or the reason I have brown hair and brown eyes. But when we talk about the expression of a trait from a protein, proteins make up all the traits we see. And so we're going to jump into the central dogma theory now. As always, you are going to need your notebook and a pencil and a pen. So make sure you have that out. If you need to pause me, pause me. And our guiding question for the day: how does an organism's genetic makeup determine the physical characteristics and function of that organism? So how do we go from DNA to what we see? The goal, and everyone should be writing this down right now. The goal, or what the central dogma theory is explains how the instructions in our DNA are expressed into our physical appearance. So how do we go from A's, T's, C's, and G's, which are the instructions that tell my body to be, well, here's Miss King's brown eye. So how do we go from here to here? And so that's what our goal is from today. And weirdly enough, it is essentially these 3 steps. And so based on our last picture, we're only adding one thing, but that one thing is really important. And so the central dogma theory is you always start with your DNA. From your DNA, you make a short strand of RNA, and that RNA then creates the protein. So this order of these 3 steps is exceedingly important, and it will show up on your exit ticket. So make sure you know it starts with DNA, where all the instructions are. RNA, which is a short snippet, it's a copy of our DNA, and the RNA goes and translates into a protein. You just did this, and it's a really good check. Check your notebook to make sure that this is all what you have. But the biggest things, the differences between DNA and RNA, is that DNA is double-stranded. RNA is a single strand, so it's basically 1/2 of your DNA. The sugar we know is deoxyribose in DNA and ribose in RNA. And the other really key difference to know is that instead of T that we have in DNA, that thymine, we actually have a U, which is uracil. But the base pair rule still applies. A always matches with T in DNA, but this time in RNA, A matches with U when it comes to RNA. And that will come up tomorrow in class, but just make sure you know that in RNA you use U and not T. But the question I always get asked is, why do we even need the RNA? If the DNA has all of our instructions and we need to make a protein, and that's the instructions for the protein, why can't we just use DNA? Well, to be first and foremost, there's only one copy of DNA. It's really, really large. But RNA can have many copies. So you can copy one strand for a protein 1,000 times. And so you can have 1,000 instructions on how to make that protein. So you can make lots of proteins all at once. So RNA can have many copies, while DNA only has one in your cell. The other thing is DNA is large. It is huge. We've talked about if you stretched your DNA out, it was like 6,000 million miles long. RNA can be really, really tiny. And because it's a single-stranded and because it's small, it can actually leave our nucleus. Our DNA can't leave the nucleus. It's stuck in there. And if you're trying to make a protein, ribosomes are only located on the outside of the nucleus. They are not located on the inside. So in order to make that protein, you need to take that instructions out of the nucleus. So 1, we can make lots of copies of RNA. 2, RNA is small, single-stranded. And so that is why RNA is that middle step into making a protein in order to express that trait. Again, pause me, make sure you copy these down. Finally, returning back to this idea. So now, you know our instructions are in our DNA. You now know that RNA is used as this intermediate or middle step to make sure that we are making lots of copies of the protein all at once. So it goes DNA, RNA, and then to our proteins. We are going to dive into what's actually happening at the molecular level with this transcription and translation from DNA to RNA and RNA to proteins. So essentially what's happening at each of these arrows over the next week. Before you jump to your exit ticket, make sure you go back to your classwork and answer these 2 really short questions, only 2 questions, and then jump straight to your exit ticket right here. That's all for today. Reach out if you have questions, jump in on the Zoom call. I'd love to hear and talk from you. I'm more than happy to talk you through the entire lesson if you'd like, but have a great rest of your Tuesday. Stay awesome and stay safe.